an X bar, a means analysis, just like we've done we've done other sort of analysis, T's and X bar. Primarily, we've worked with means up to this point, but now we're going to work with the variance. Okay, and so it's going to be the exact same thing. We're going to have a variance for a population. Okay, and then we're going to have a variance for a sample. Okay, and if you don't have the variance for, if you're trying to estimate, if you're trying to determine the variance for a population and you don't have all the numbers for a population, what do you have to use? Yeah, you have to use a sample. And so every time you introduce sample to any situation, what do you pick up? What does that cause? What problem does that cause? That's exactly right. Right. That's exactly right. It's less accurate. And in statistics, what is our measurement of less accurate as you know it today? Mitch. What is it? Close. Actually, it is close. Variance is in the equation, and I think that's what you were saying was variance is in the equation associated with alpha. I think that's what you were kind of yeah. Alpha. We know it as alpha, or our p-value, our sig level, right? So we're going to do it's going to all be the same. The only difference is we're going to be dealing with sigma squared or s squared instead of x bar or mu. It's the only difference here. And we're also going to use some different tables. But the good news there is those same tables those tables are also loaded into Excel or Minitab. Okay, and Excel doesn't do a very good job at chi-squared. That's a little bit of a Schulteism. So there's much more sophisticated software after Excel in order to work with variance analysis. And in fact, once we talk about variance analysis here, and we're only talking about two variables. Okay. When you get to three variables, you move into what's called an analysis of the variance, an ANOVA, okay? And that's probably where most of you will pick up as far as the advanced course goes. So this is a prelude to the ANOVA, okay? Chi-squared is in there as well, but really the analysis of the variance, we take two variables, we look at them, okay, or two sigmas, sigma squared, we look at them, but what if you have three sigma squared? Okay, you'd have to run multiple variance analyses, and it's like, why do that? We'll just go to an ANOVA. Okay, and everything's working again. I don't know what is going on. This is like crazy. So we have a population variance, and we have a population variance just like we had a difference between an X bar and a standard. Remember we had instead of comparing two mu's, we compared mu to a standard of 30 units. The minimum was 30 units, or 30 pints, or 30 whatever. And so here we're going to do that same thing, okay? And then we're going to compare two population variances where we're actually going to compare sigma squared 1 to sigma squared sub 2, or s squared sub 1 to s squared sub 2. And then in the end, we're going to do we're going to start moving into a little bit more chi-squared orientation and f-value analysis, and you're going to get an S1 and an S2 where you're only working with the standard deviation. And so why would we want to do this? We would want to do this because the variance, you can use variance to understand what's going on in many, many situations. They talked here about filling containers with liquid detergent product, okay? Kind of that you could probably do with an X bar, but when you're getting into high-end machining or very intricate sort of analyses, okay? Understanding if there's just a slight variance in a temperature associated with a manufacturing product in the pharmaceutical business could be huge. Just too much variance could throw your whole production line off. So that's where That's where we can use variance analysis. And you can also use it here with just liquid detergent product and filling weights and things like that, depending on how much variance. And if is less variance better or worse? Why? Exactly. Precisely. That's great. That's right. It's more accurate. However, sometimes it's too expensive to be accurate. So you're right, but other times, if you get too accurate, it's like you're wasting a lot of money, because this is just, we're just talking about laundry detergent here, right? Okay. All right. We're not talking about high-end machining. We're not talking about the pharma business or anything like that. Okay, so you can actually determine how much error you have. It's an error issue. Variance is an error. Okay? Or how much dispersion you have, or it's a function of error. Yeah, it's a function of error. Let's call it a function of error. A little bit of a Schulteism there, potentially. And so we're going to look at three different sort of approaches here. All right? I'm not going to spend a lot of time on interval estimation. What I'm going to do is I'm going to spend most of the time on hypothesis testing, because that is what we do as business people. You have a pre-test and a post-test. This is so classic. This is what you'll do, whether you do it by the numbers, whether you do it mathematically, whether you do it by gut. You're always looking at, here's time. For the most part, you're looking at time, and here's time, and you're coming along, and this is your volume of sales. And you say, hey, you know what? I'm going to put in this new sales plan. Right here. Okay? If sales go up, is that good or bad? That's always good. Yeah, most always good. Right? If sales go down, is that good or bad? Most always bad. Mitch, do you agree with that? You do agree with that. You're being a good sport. Thank you. All right. If sales go like that, ooh, probably not good. You're just wasting your money. If it's a new sales plan, it's going to cost you a little bit more. And so on this one, which one is HO? Of these, well, let's take this one out. Of these, which one is, let's take this one out. Of these, which one is HO? The dotted line. Which one is the alternate? There you go. Pre-test, post-test. And that's why we focus so much time on hypothesis, because that's what we do every day. If you're trying to decide whether you're going to do something versus another thing, you're always doing a pre-test, post-test, whether you know it or not. You're doing that analysis. If you're sitting there going, okay, I'm going to write out a pre-test, post-test on making the decision on whether to buy a car or not. Now you know. That's when you know that you're a geek, a serious geek. If you just make it by gut and you go, hey, I've got some money and I think it's going to be better, then you're a normal person, potentially. Which could be good or could be bad. Sometimes it's good to be a geek. Geeks rule the world. Think about that. So what we have here is we have normal distribution. We still have normal distribution, except that there's going to be a little bit of a difference here. With chi-squared distribution, you don't get a negative value. As you recall, with the T's and Z's, we got negative values. Here you don't get negative values. Everything has to be a positive number. And the level of positiveness matters. From a normal population, random selection is still absolutely key in this testing scenario, just like we did when we're doing T's and Z's. It's the exact same thing here. In fact, on any statistical test, almost always, normalcy of distribution and randomness of sample are the underpinnings of whether or not you can rely on that data or not. Or if the findings have some invalidity associated with it. That's a whole other course. And as before, the closer you get to the population, are you going to be more of your sampling? The closer you get to the overall population, are you going to be more accurate or less accurate as far as understanding what's going on in the population? More. Absolutely. Every time. And when you get to the population itself, what have you eliminated? There's no error. The sun's going to come out tomorrow. 100% probability. Here again, don't get too, as you've hopefully come to understand, or we're moving toward, don't get too wrapped up in a lot of these formulas, because the computer's going to do this for you. You're not, I mean, even if you're doing business analytics, the computer's going to do it for you. You have to understand what's going on. For example, here, the shape of your distribution curve, the area under your curve, from a probability perspective, changes as your sample size goes up. And that's all that's happening here. You're going from 2 degrees to 5 degrees of freedom. Your sample size is going up. And as your sample size goes up, you come closer to a normal distribution, which is, hopefully that's the next one up. And now you have something that looks a whole lot more like a normal distribution with not much skewing. You don't see much tail activity going on there. You see not a lot of kurtoses potentially. Nice distribution. And for chi-squared, it's not chi. Some people call it chi-squared. I think one student kept calling it chi just to kind of needle me a little bit, but that was a long time ago. And so this is actually called chi-squared, and this is a Greek symbol for chi. All right. And so there is a probability associated with a chi-squared, and the reason we would use chi-squared instead of t is why? It's because you're dealing with variance instead of means. You're dealing with, again, it's an accuracy issue for sure, but now you're really you're kind of a little bit deeper into the understanding of how much error you're really picking up in some respects. We can do an interval estimation, as always. That's the interval estimation. This is a two-tail, and you put p.025 up here. It's actually 0.025 up here, 0.25 up here. And here's the way you do that. And so in between here, what is that called what is that area called in a means test analysis or a t-test? What zone is that called? Huh? Do not reject HO. That's right. That's right. And when you fall out here, what happens? Reject. Time to write home to Aunt Donna, because that's the only way she wanted to hear from you. She likes you, but not that much. You're her favorite. You're her favorite nephew, aren't you? Oh yeah, there you go. So when we're doing these variance analysis, we have the same type of discussion, HO, HA. Here is the equality. As we know, equality is always a part of, always a part of the discussion for null. It means there's no change. And here, this is a one-tail analysis, and we're using null that it's greater than. And then we create, here we go. We got our test statistic, step 2. Actually, that test statistic is step 3 of our 5-step process. We would, before this, what would we have to do before this, before we went to a t-statistic? What might we have to do? Kinda. You want to determine your bogey. Yeah. P.10, P.05, P.025. I agree with you. Played well, sir. I'm going to give that to you. Should we give that to him? Oh, okay. See, Mitch, you should just, yeah, you should have just taken it before. So, and here's a left tail. Same old, it's just a different flavor. That's all we're doing here. And instead of using means, we're using variance, which is a measure of accuracy, or how much, not accuracy, but how much dispersion you get in your distribution or in your test results. Here's our old friend, degrees of freedom. All right, and the good news here, I don't think we do any blending in chi-square as far as degrees of freedom, which I think is probably a good thing for most people. Certainly us, but now that we know how to run the computer, doesn't matter. Here's a right tail test. Same thing we've talked about before. The only difference is instead of having x bar, or instead of having mu up here, these are now sigmas, and we use sigma because that's the standard deviation for, or that's the in this case it's the variance for the population. So we're going to do what we're going to do here again, because we're doing sampling, we're always doing a point estimate, and the question becomes, does our point estimate based upon a sample, what is the probability that we include, in this case, the population variance with our sample variance? And there's always going to be a chance you're wrong because you're always dealing with samples. And so we're most here, and in this case again, we're going to usually run p.05. Everything, when in doubt, okay, if you see something on a test, or let's put it in a real workaday world, okay, and somebody comes in and says, hey, I need for you to run an analysis, a statistical analysis, and get with Shane, get with the business analytics people, and the person most likely is not going to say, hey, and run that thing at a p.05. They're going to say, they're going to go, they're probably not, you're going to be the smartest people in the room, seriously, for the most part, except for maybe the business analytics person that works with it every day. And so you're just going to naturally default to p.05. There's a 5% chance you're wrong, but there's a 95% chance you're right, and that's generally how business decisions are made, unless, as we've talked before, you're in the entrepreneurial world. Then you're down around that p.5 that we showed before. Your test statistic as normal. Here's your rejection rule. And here we come to our old friend p-value. That's why on any report, any printout, the first thing you want to look for are the p-values. Now, when we start getting reports, there's going to be a lot of information. You got to make sure you're looking at the right p-value. Are you looking at the p-value? And this is going to be the discussion as you get further and further, certainly into ANOVA, regression, multiple regression, legit, on and on and on, that you'll be covering in the advanced course, is that you want to make sure you're looking at the right p-value, because there's p-values associated with the individual variable, and then there's a p-value associated with the overall model. So it all depends which one you're looking for. And there are ways to quickly determine that. But the key to just cutting to the chase of all, everybody's going to talk, oh, what's the f value? What's the chi-squared? What's the t value? And it's like, well, I'm guessing it's pretty good because there's a p.03 here, and at p.03, there's something happening. A heuristic of sorts. And here's a two-tail analysis. How do we know if there's a two-tail versus a one-tail analysis? Yes. Jessica, go ahead. How do you know if it's a one-tail versus a two-tail? Yes. Yeah. And if you get a sense of direction, are you a one-tail or two-tail? If you get a direction, are you doing one-tail or two-tail? That's exactly right. Exactly right. And if you see there is no difference, they're the same, are they the same, you have no direction. Well done. Well done. And here's your two-tail. A little bit different. And here we come again. You look for that p-value. That's going to tell you where any research project, any study is heading, if they're using a sample size, or if they're using a sample of the overall population. Let's grab an example here. What's going on here? We have a thermo right. It's a thermostat. And if you're a thermostat and that thermostat is being used in an industrial application, is a lot of variance good or not so good? Probably not good. With beer, I can assure you, with beer, they measure this down to the tightest variance they can afford. And I'm using beer, but also that applies to many, many other things, including pharmaceuticals for sure. Legal pharmaceuticals, I might add. And so we're going to conduct our test at P.10. And we want to find out if that variance, our sigma squared, is P.5 or less. You see P.5 or less, are you one tail or two tail? Or you see a 0.5, it's not a P, that's a 0.5 or less on your variance. Is it a one tail or two tail? Jake.
Sorry?
Is it a one tail or one tail?
Is it a one tail or one tail?
If I use the term or less.
What's the one tail?
Excellent. All right. I had your back there, you know.
Yeah.
Yeah.
You just had this one tail or one tail.
Yeah, I had your back.
You gave me one option.
There you go.
Take it.
Every time.
Because it gives you a sense of direction, right?
Even better. I'm going to send you flowers one of these days. And you're doing great. All right. Don't take that the wrong way. And so you want to find out if it's acceptable or not. You're going to get 10 readings. What's 10? What does 10 represent? Your sample. Exactly. Every time. 10 readings. P.10. Your bogey is on a variance is 0.5. I think it was 0.5. Was it 5.5? Yeah. Not to be confused with 50%. That's an actual variance, not the p-value. And you're going to determine if that's acceptable or unacceptable based upon the standard. You come in here. Here's your handy dandy numbers for temperatures, and you run those numbers. And by the way, degrees of freedom calculation will not be on the exam. Okay, thank God. I agree. I agree. That was painful, but it was a good thing to go through. No pain, no gain, just like in football or any other sport, right? No pain, no gain, just like. Okay, so we're gonna do a one-tail analysis, and so our HO is less than or equal to 0.5. Here's our rejection rule, and here this is chi-squared, and that chi-squared value is your chi-squared at P.10. And here is your actual chi-squared value, 14.64. And here is your chi-squared chart. And if you go to the back of your textbook, you will see this chart. I think I've torn mine out about 1 million times. So go to the back of your textbook. Somebody call out the page when we get there. 979. There we go. 979. Yes, that's right. 979. And you will see that table on 979, page 979 in your textbook. And we knew the way you come up, and this is a critical, you're creating the critical values. This is step 4 in a critical value analysis. And we say, okay, degrees of freedom was 9. We're going to go a P.10. It's not a two-tail. We come down here and we go 14.684. And it's the same old, same old. The only difference between at least the distribution on chi-squared versus what we've talked about before, x bar, is that this chi-squared with a normal distribution, you're never going to get a negative value. You can't go here. It doesn't exist in the chi-squared world. And you say, now you go, okay, is this an upper tail? Yeah, this is an upper tail. And we go 14.684 in the upper tail over to the right side, way to the right. And so now we know that this value out here in the reject is P less than .10. This is the do not reject. We're setting up the exact same model. And it's getting to the point now where we don't even have to use props, right, Caitlin? I mean, you know where this thing's going. We don't even have to call a cup a test statistic anymore. We can just go for it at this point. Let's see if it works. There's your rejection region, right out here. Anything down here? What's that? Do not reject. And what does P.10 represent? A certain amount of error that you're always going to pick up. And as long as you're less than that P.10, that's your standard, you're golden. What else is in there? And here we did the chi-squared sort of analysis, or crunch the numbers. So we did our test statistic. It's 12.6. Okay, let's try doing this let's try to do this without our crutches here. Does anybody have a crutch? We can use that as a test statistic. Okay, nobody has a crutch. Okay, so now we have our test statistic of 12.6. What was our critical value? 14.65. All right. Now close your eyes. Imagine your test statistic going against that model that's up on the board, or that we saw just before. Where do you fall? Do not reject or reject. You can open your eyes now. Do not reject. That's right. Exactly. So now what do you know? Yeah, that's exactly right. So what would the business decision be? Coming out of the kind of the muck or the woods here. You going to take that thermostat or not? Yeah, sure you would. Yeah. It's acceptable. There's no evidence to say that it's unacceptable. So you're the purchasing person, real world, you're the purchasing person, and this was the requirement, is that there can't be more variance than a 0.5. We did a sampling, and therefore, if you're the purchasing manager and somebody said, go out and get some thermometers with this spec that's no more than 0.5 variance, you're going to buy this or not? Probably, assuming it's not too expensive. That's the business decision. That's where and you'll see that as you get into, hopefully, well, for sure you'll get it when you get into the real world, but hopefully you'll get that in your advanced course, is that the numbers, it's important. It is important. But interpreting the numbers is what we as business people do. That's what we do for a living. Or you as business people. I'm in academia now, so I can do whatever. So now, and where would you expect, if you do not reject HO, what would you expect that p-value to be? Less than P.10 or greater than P.10? If P.10, where's your standard? Greater than. Why?
Because if it was less than, then it would be rejected.
Yeah. If it's less than P.10, which is your bogey, there's something to write home to is it Donna? Aunt Donna about. But if it's greater than P.10, don't bother me. I love you as a nephew, but don't bother me. I don't want to hear from you. You're being a good sport. Thank you. We cannot reject the null hypothesis. Therefore, it says the same thing. And in fact, when you run the numbers, it's going to give you the exact p-value, so you don't have to guess or extrapolate. We don't want to do extrapolation here. That's no fun either. Okay. And the computer will actually give you this. If you calculated this out, it actually come out to 0.18, which is that greater than P.10 or less than P.10? Greater than. If it's greater than P.10, what's your aunt's name? Jane? If it's greater than P.10, you're going to write home to Aunt Jane? No. No, she don't care. I mean, she loves you, man, but she said only call me if you got something. Are you okay? Okay. So what I want you to do is go to 11.3, page 491. That was a big lead up, and that is probably the last long lecture of 32 minutes that you're going to be hearing from me. And in fact, the last two classes you're going to be hearing from yourselves. So, and by the way, that schedule is out on as far as who's presenting when. I think that we had room for 8 teams. 8 teams. We're going to do 10 minutes apiece or less.
Yeah, I got the email. What is
Yeah, there's only 2 teams going on Thursday. I think it was team 2 and 3. I picked out 2 of them. One was I think one was just a quick, or one was a analysis of a single means, and the other one was a comparison of the means. And the reason I picked those 2 out at the end was because that's going to be the meat. That really is going to be the meat of this exam, is being able to compare means or compare a mean to a standard.